All right, welcome. Today we are diving into the legendary problem collection by E.I. Irodov. We're going to be tackling problem 1.25, one from the kinematics section. Now, this one's a challenge, for sure, but it's also incredibly rewarding, and it's a fantastic way to sharpen your physics fundamentals. So, let's get right into it. Okay, so here's the problem in all its glory. We've got the motion of a point in the xy plane, all laid out as a function of time. And it's asking us to find three things. First, the actual path it takes, then its velocity and acceleration, and finally this really specific moment in time when those two vectors form a 45-degree angle. I know, it looks like a beast, but the beauty of a problem like this is that we can break it down and solve it methodically, one piece at a time.
So here's our game plan for this explainer. We'll start by talking a little about what makes these Irodov problems so special. Then we'll jump into part A and figure out the trajectory. After that, part B is all about finding the velocity and acceleration. And to finish it off, we'll tackle that vector angle in part C. Then we'll wrap up by recapping the super powerful tools we used. Let's do this.
Now, before we start crunching the numbers, it's worth taking a second to appreciate why Irodov's problems are so famous in the first place. See, they're not just about getting to an answer, they're specifically designed to build a really deep, kind of intuitive understanding of the physics behind the math. So as we're solving this, remember, we're not just doing algebra, we're building our physics brain.
Okay, let's dive into part A. We're given the particles x and y coordinates, but they're both in terms of time. Our mission is to find the actual shape of the path, its trajectory. To do that, we have to get rid of the time variable. We want to find a direct relationship between y and x. It's like taking the stopwatch out of the equation and just looking at the path traced on the ground.
So that's the big question, right? How do we take these two separate equations, one for x and one for y, that both depend on time, and squish them together into one single equation that shows how y depends on x? Well, this process has a name. It's called parameter elimination. And in our case, the parameter we're kicking out is time. And the strategy for doing this is actually pretty straightforward. It's a simple three-step recipe. First, we'll take the easier equation, the one for x, and just solve it for t. Then, once we have an expression for t, we're going to plug it into the y equation everywhere we see a t. After a little bit of algebraic cleanup, we'll have our answer.
And voila, after that substitution and a little simplifying, we get this beautiful equation right here. Now, the most important thing is to recognize the form of this equation. You've got y equals some term with x minus another term with x squared. Does that ring a bell? It absolutely should. This is the classic equation for a parabola that opens downwards, the exact path a projectile takes when it's moving under a constant downward pull, just like gravity.
All right, on to part B. We know the shape of the path now, but how is the particle actually moving along it? Is it speeding up, slowing down? To answer that, we need to find its velocity and acceleration. And to get those from our position equations, we have to use the powerful language of calculus, specifically derivatives. This is where the math really starts to tell us a physical story.
The fundamental principle here is super simple. Velocity is just the rate of change of position over time. Since our position is a vector with both an x and y component, we find the velocity vector by taking the time derivative of each of those components one by one. So let's look at the components. The derivative of x equals z with respect to time is just the constant a. What does that mean? It means the horizontal velocity never changes. It's constant. Now for the y component, the derivative gives us a minus 2a alpha t. That t in there tells us the vertical velocity is changing. It starts at a and then decreases as time goes on. And when we put those two pieces together, we get the whole picture. We use the unit vectors I and j as little labels for the x and y directions. And there it is, the complete velocity vector as a function of time. This thing tells us everything, both the speed and the direction of our particle at any moment. And the logic just keeps on rolling. How do we find acceleration? You guessed it. We do the exact same thing again. This time, we take the time derivative of the velocity vector we just found, because acceleration is simply the rate of change of velocity. And just look at this result. This is awesome. When we take the derivative of our velocity vector, that constant x component just becomes 0, and the y component gives us another constant, negative 2a alpha. So the acceleration is constant, and it points only in the negative y direction. This is a huge aha moment because it perfectly confirms what we suspected back in part A. The particle is moving just like a projectile under gravity, where the acceleration is constant and points straight down. It all connects. And now for the final piece of this puzzle, part C. We need to find that one specific moment in time, which we'll call t0, when the velocity vector and the acceleration vector are at an angle of 45 degrees to each other. So this isn't about how fast it's going, but about the geometry of its motion vectors. So this begs a really important question. What's the go-to tool in our mathematical toolbox for finding the angle between two vectors? If you're thinking about the dot product, you are absolutely on the right track. The dot product is perfect for this job. You see, it has two different faces. One way to calculate it is to just multiply the matching components and add them up. But the other way involves the lengths, or magnitudes, of the vectors and the cosine of the angle between them. By saying these two things are equal, we can build an equation and solve for whatever piece we're missing, which, in our case, is the time. So here's our plan of attack. We set up the dot product equation for our velocity and acceleration vectors, and we plug in 45 degrees for the angle. Then we calculate the dot product using the vector components. After that, we calculate the magnitude, or length, of each vector. We substitute all those pieces into the formula, and the only thing left that we don't know will be t. From there, it's just an algebra problem. And after working through all that algebra, we get this: a remarkably simple and clean answer. The exact moment when the velocity and acceleration are at a 45-degree angle is simply 1 over the constant alpha. How cool is that? A really elegant result for a pretty complex question. So we've done it. We've solved the problem. But before we go, let's just take a step back and recap the methods we used, because this wasn't just a random bunch of steps. We applied a core set of really powerful fundamental techniques. Think of it as your essential kinematics toolkit. Think about what we did. We used parameter elimination to find the actual physical path. We used differentiation twice to get velocity and then acceleration. We pulled out the dot product to answer a geometric question about vectors. And maybe most importantly, at every single step, we stopped to interpret what the math was telling us about the real-world physics of the motion. These 4 techniques will help you solve tons of problems in physics. And that brings us to one last thought. We saw how perfectly this problem describes projectile motion. But could it represent something else too? What about, say, a charged particle entering an electric field at an angle? I'll just leave you with that question to chew on. Thinking about how the same math can describe different parts of the physical world, well, that's what makes this all so fascinating. Thanks for joining me on this one.